All right, welcome back again. Today we're going to be doing section 12.2. This one is all about vectors. I think some of you may have learned about these before in a physics class, so some of this might be review, but I'm sure much of it will not be review. Let me go ahead and pull up the slides and we'll get started. All right, so in the last section we talked about three-dimensional and just n-dimensional space. Now in this section we're going to talk about vectors in all dimensions, but with an emphasis on dimension 3. So here's the overview. Just going to talk about vectors as telling us direction in space. Then we'll talk about geometric vector arithmetic, then algebraic vector arithmetic, then basis vectors, unit vectors, and then one quick physics application. One thing I want to say is the comparison between these two. So a good thing to keep in mind is with everything we do, there's basically a geometric interpretation and an algebraic interpretation because algebra and geometry are connected in very intimate ways. So it's good to think about things in both ways, the geometry and the algebra. All right. First off, just what is a vector? So just as we saw with the Cartesian coordinate system and points to describe locations, now we need a way to describe direction in space, like where to go and how far. And this is what vectors are for. So what is a vector? A vector is a geometric object that has both magnitude and direction. That's basically it. Here is an example of a vector V. A lot of times we'll use an arrow to represent vectors, but intuitively a vector just says which way to go and how far to move. So you could imagine this vector here as saying go in this direction and go this far in that direction. That's what a vector really is. It's got two parts to it. It's got a direction and a magnitude. Geometrically, we often use arrows to represent vectors, and the length of the arrow can be used to represent the magnitude of the vector, or basically the size of the vector. Symbolically, if we want to write things down, we either use a bold letter like V, or we use a letter with an arrow over the top of it like so. Um, I will probably start by using just the arrows when I want to write them down, but to be honest, I tend to forget to use the arrows sometimes, so the context will be what you have to pay attention to. All right, so what is a displacement vector? If a particle moves from a point A to a point B, then the corresponding displacement vector V has an initial point A and terminal point B. And what we do is we write V is equal to this right here, basically the vector from A to B. And quite literally, it means exactly that. Start at the point A, go this far to the point B, and that's called the displacement vector. Two vectors are said to be equal if they have the same direction and the same size. So this is a picture of two equivalent vectors. These two arrows that you see on the screen right now, those are considered the same vector, even though they're not in the same place, all right? But they're equivalent because they both say to go this way, this far. That's the idea. The zero vector is denoted by a bold zero or a zero with an arrow over the top. And it's the only vector that has no specific direction. It is unique in that way. The zero vector is the only vector that doesn't have a direction. Okay. All right, now let's talk about some geometric vector arithmetic. What's nice about this is it's very intuitive, and you've been doing it a lot on your own, maybe not even realizing that's what you were doing. So here's an example. If we have two vectors, say u and v, and we want to add those two vectors together, then what we get is that the vector that goes from A to B and then from B to C is equal to the vector that goes from A to C. Geometrically, this is what's going on right here. All right, so intuitively what's happening here is adding two vectors is basically like adding two arrows together and connecting them tip to tail. Or maybe I'll try to copy the picture here, tip to tail like that. So this picture is a really good example. If you want to do u plus v, it's saying travel in the direction of u, and then from there, travel in the direction of v. And what this is saying is that when you do that, that is the same as traveling from here to here. You get the same result. You end up in the same place. That's the idea. So u plus v is equal to the same as going from A to C. So basically it's like saying go from A to B and then from B to C. That's what vector addition looks like geometrically. Now let's practice this one. So let's sketch the sum of the two vectors A and B pictured below. So we're going to draw a picture of it. I'm going to utilize my technology here. Let me pick a color blue. So I'm going to cheat a little bit by using my using copy paste. That's what I'm going to do. All right, so I just traced over those two vectors. Actually, let me A, B. All right, let me go ahead and highlight these. Okay, so here's the vector A, and here's the vector B, and I'm going to add those two vectors together. So what does it look like? Well, if I start with A, I'm going to travel in the direction of A, and then I'm going to travel in the direction of B from there, and this is the point that I end up with. So I started here and I went, and that is the same as going from here to there. So this is the vector A plus B. Oh, there you go. See, I forgot the arrows already. There you go. I mean the arrows on top of the. So that's what it is. In fact, maybe I'll move this out of the way a little bit. There. So geometrically, this is what A plus B looks like. That vector addition. All right. So scalar multiplication, one thing we can do with vectors is we can scale them, and we scale them by multiplying them by a scalar. So what is a scalar? A scalar is, for us, it's a real or possibly a complex number. We're going to stick to real numbers for the most part, but a scalar is just a type of object that has a certain property. Just think of it as a real number. A scalar is a real number, but we could also use complex numbers if we wanted to. So if k is a scalar and v is a vector, then the scalar multiple k times v is the vector whose length is k, absolute value of k, times the length of v, and whose direction is the same as v if k is positive, or opposite of v if k is negative. If k is equal to 0, or if we're dealing with the 0 vector, then kv is equal to 0. Intuitively, what we're doing is we're literally just scaling the vector. We're stretching it or shrinking it. We're not changing its direction, we're just changing its length. That's all it really does. Maybe I'll copy the picture. There we go. We're just changing its length. So for example, here is the vector v in the middle. And if I take that vector and I want to shrink it by a half, I get half of v. So going from here to here is like multiplying by a half. And that shrinks the length. Oops, shrinks the length. All right, if I want to stretch it out, so maybe I want to stretch the vector out, well, I just multiply by some number, like 3/2, and it pulls the vector, makes it a little bit longer, like taffy, right? There you go. In both of these cases, k was actually positive. So if k is positive, then the direction of the vector doesn't change. It's staying pointing the same way, but it might get stretched or shrunk down. Now, if k is a negative number, like -1 or -1/2 or negative anything, it's not only going to scale the vector, the length of it, but it's also going to turn it the opposite direction. Kind of doing it there. Yeah, it's going to go in the opposite direction. So for example, -v is the same length as v, but literally going the opposite direction. That's it. So that's why we call it a scalar multiple. It's literally scaling it, and that's how you do scalar multiplication on vectors. All right, so what are parallel vectors? So we consider vectors to be parallel if there is some scalar multiple, sorry, if they're scalar multiples of each other. So for example, if we've got a vector A and a vector B, and we can find a scalar, like a real number k, such that B is equal to k times A, that means they have to be parallel. That's really it. So notice, for example, in this picture, all of these vectors are considered parallel vectors. They're not equal. So that's one thing. They are not equal and they're not equivalent vectors because their size is different, but their direction is the same. So parallelism isn't really about size, it's about direction. And in all of these cases, the vectors are, I should say this one's the opposite direction, right? So pretend this one is hidden for a minute. These ones are all pointing in the same direction, but they're different sizes. So they're all parallel. This one is also parallel because it's literally just like the opposite. So how do you define this algebraically? We say two vectors are parallel if there's some scalar where you can write one as a scalar multiple of the other. That's it. What's a negative vector? A negative vector is just a vector that goes in the opposite direction of the original vector. So the vector negative v is the same as multiplying v by the scalar -1, just to flip it, right? It's got the same length as v, but it points in the opposite direction. So we call it the opposite of v, or we call it the negative of v. So here's v, here's the opposite of v. There we go. Okay, now that we've talked about scalar multiplication and vector addition, vector subtraction is basically just written as adding a negative, so there's not much to it. You just add the opposite. So we're going to do another example here where we're going to sketch the vector a minus 2b given these vectors below. This is one where I actually encourage you to try it on your own if you can. Just make up your own vectors a and b. They don't have to be exactly like this. Just draw a couple arrows on your paper or on your iPad or tablet or whatever, and try to see what a minus 2b is going to look like. All right, think about it for a minute. Right, then say out loud to yourself how you're going to compute this, the result of this geometric vector subtraction. All right, now try it out. Draw your two arrows, your two vectors a and b, and compute visually, geometrically, what a minus 2b is. All right, now let's do it together here. Let me get my pen here. Okay, I'm just going to copy these. Okay, so I got the vectors a and b copied. A, B. Just move these out of the way for a minute. All right, so there's a and b. This part, I already got vector a picked out. Now I need to show the vector -2b, and then we're going to add those two results. So I've got the vector b. If I want the vector 2b, I just need to double the length of b. So I'm going to do this. Again, I'm going to use technology to my advantage here. Copy, paste. There you go, tip to tail there. And now this is the vector, there we go. This is the vector 2b. Right, move that over there for a minute. Now I've got the vector 2b. However, I want the vector -2b. So I basically need to take this vector and go the opposite direction, which I'm going to do like so. Oops. Come back, come back. Okay, pretend that's a straight line. Wait, I can use technology. There we go. -2b. All right. So what is a minus 2b? Well, I'm going to take the vector a, and then I'm going to go -2b from there. So then we get this right here. Actually, give myself a little more space. Here we go. So we're going to go from the tail of a all the way up to here. There we go. And this is the vector a minus 2b. And that's what it looks like. So that's geometric vector arithmetic, just like that. Okay. All right, so now what does this look like algebraically? So let's go back down to 2 dimensions for just a minute. If we've got a 2-dimensional vector, A, and we place the initial point at the origin right here, then what we can do is we can say that the terminal point lies at the point A1, A2. So the vector here is denoted by A1, A2 with these little angled brackets, a left angle and a right angle. We use those to denote vectors algebraically if we want to look at the components of each vector and then operate on those components. This vector that you see here is what we call a position vector. It's a position vector, and the coordinates a1 and a2 are the components of the vector a. So this is the first component, the second component, If you put the tail of this vector at the origin, then the tip is at the point A1, A2. So there you go. All right, that's basically it. Same thing happens in 3D. So if you're, or ND. So if you're in 3D space, then you just happen to have three components of your vector. And the same things hold. If you put the tail at the origin, then you get that the tip is at the point A1, A2, A3. This is the position vector. In general, in n dimensions, same thing applies. So we could have a vector of n dimensions. Oops, sorry, this should be a capital right there. We could have a vector of n dimensions, and that's what it looks like. If we put the tail of it, if we put the initial point of it at the origin, then our terminal point will be right here. All right. Now, one important point, pun intended, is this. Vectors are not points. So if you've never worked with vectors before, this can be a little bit awkward to get your head around, but vectors are not points. They are not the same as points. They are not points, so you don't treat them like points. What they are is they are directions and distances. So this is basically a new quantity that we're working with, a new mathematical object that is different from a point. This is actually why we use the angle brackets, just to distinguish the notation from a point. Later on, the notation will get ambiguous in like your later classes, but just understand that vectors are not the same as points. All right. So for even more clarity, we write v sub n to denote the set of all n-dimensional vectors. So for example, v sub 3 is the set of all vectors in 3 dimensions. So vectors that have 3 components to them. So notice that this is actually distinct from Rn, which is the set of all points in n-dimensional space. There you go. So there is a distinction between vectors and points. Actually, this diagram here is a good illustration of it. So every vector that you see in this picture is equivalent. These are all equivalent vectors. These are all treated the same thing, because a vector is just a direction and a distance. That's all it is, right? But this is the position vector. This is the position vector. All right, so doing some algebraic vector arithmetic, how do you get the displacement vector when you know the components? Well, if we're given 2 points, A and B, then the displacement vector that goes from A to B is given by just taking the difference of the respective coordinates. So x2 minus x1, y2 minus y1, z2 minus z2 minus z1, and that's the vector. So this makes sense. The reason this is called the displacement vector is because x2 minus x1 is literally the displacement in the x direction. y2 minus y1 is the displacement in the y direction, and z2 minus z1 is the displacement in the z direction. And that's why we call this the displacement vector. So in essence, these are just telling you how far to go and in which direction along the coordinate axes. Okay, basics. If we've got 2 vectors, then vector addition in its algebraic form is exactly what you would expect. You just do everything component-wise. So A plus B equals A1, A2, A3 plus B1, B2, B3, and the addition occurs component-wise. So A1, B1, A2, B2, A3, B3, so vector addition occurs component-wise. Same thing with vector subtraction. And then scalar multiplication is also component-wise. So I guess the moral of the story here is that this is really just happening component-wise. So k times a is just applying the scalar k to every component, like so. That's what it is. Now, one of the cool things is that this totally agrees with our geometric intuition or our geometric interpretation, right? So, for example, here we go. There we go. So this is the vector a plus b, right? Here's the vector a, here's the vector b. We saw how to add those geometrically to get that vector right there. Well, let's look at the components, the corresponding components. This is the component a1, and this is the component a2. This is the component b1, and this is the component b2. So what do? You literally do, or is it? Is that right? Yeah. A1 plus B1, and then you do A2 plus B2, and that takes you right to that point. So it agrees with your geometric intuition. Same thing with scaling. What does a scalar do? Well, if I take A and I scale it by K, you're scaling each component. So you scale you scale A1 by K, and you scale A2 by K, and that gives you KA. All right. All right. Oh yeah, so length of a vector. So length of a vector is kind of what you would imagine. The magnitude or length of a vector is the length of any of its representations. We denote it using the absolute value symbol, or sometimes this double bar. You'll see that more in later classes. And how do we compute the length? The distance formula. It's just the distance from tip to tail. That's really all it is. So in 2 dimensions, you're going to get this. A1 squared plus A2 squared, and then take the square root. In 3 dimensions, A1 squared plus A2 squared plus A3 squared, take the square root, and that's the length of the vector, right? More generally, so again, have an eye toward higher dimensions. This doesn't need to stop at dimension 3. This can go up to dimension whatever you want. So how do you do it in general? You literally just square each component, add up all the results, and then take the square root of that result, and that will give you the length of any n-dimensional vector, right? Now here's a fun question for you to just ponder and ruminate over. How could you define the length of an infinite dimensional vector? How could you possibly define the length of an infinite dimensional vector? Ponder it, have fun with it. All right. So for this one, now we're just going to do some standard problems, just some standard algebraic vector arithmetic. Let me do this. These ones, look at them for a minute and just think about how you would compute them for just a moment here. All right, now say something out loud to yourself about what you would try or how you think it's going to work. Maybe pick one of these and say something out loud about it. Right, okay, and now I want you to try to work them out on your own. For this, I honestly like go with your gut. Remember, all of this stuff is component-wise, right? So when you're doing a vector sum, you're just adding up the components to get that new vector. So go with your gut, try to work these ones out, and then we'll look at them together. All right, here we go. We've got our two vectors listed here and here. First, we can find the length of A. I'm actually going to pull up all the answers at once. Length of A, we just use our formula, the distance formula. Square all the components, add up the result, take the square root, we get 5. So the vector A has length 5. What is A plus B? Component-wise addition. 4 plus negative 2, 0 plus 1, 3 plus 5 gives us 2 comma 1 comma 8. Same thing for subtraction. We just use where we compute the difference of the components. 3b, we just scale the components individually. And then the last example is just putting all of that together and making what's called a linear combination. So scale A by 2, scale B by 5, add the two results together, and this is what you get. Right? Not too bad, right? All right. So, oh yeah, okay, this is another nice thing about vectors. So with vectors, you can talk about starting at a point and going in a certain direction along a given vector. So this is one that I want you to try out on your own here. Let me see. Yeah, okay. So try this one out on your own. First, just think about how you would start. Right, say something out loud to yourself about how you would start. And then try to work it out on your own. What point will you end up at if you start at A and move along that vector V? All right, here we go. So it's really quite intuitive. I mean, go with your gut for a lot of this stuff. If we start at this point and then we move along this vector, then really we're just going to add those results, add these components to the point we were at, right? So if we started here, Well, this is saying start at this point and travel this direction, I'm sorry, this far in the x direction, and then this far in the y direction, and this far in the z direction. So we get this, a new point, 19, -5, -7. That's where we'll end up. Okay, next one. Oh, that's right. Also, what if it goes in the opposite direction? So I forgot about the second part of the question. What if you travel the same distance, but you go the opposite direction of v? Well, in this case, you just need to compute negative v. Negative v is easy to compute. You just apply a negative to each one of the components, and then you end up at this point when you travel in that vector, or travel along that vector, negative v. Right. Okay, so now some nice properties of vectors. Again, a lot of this is very intuitive. It can kind of go with your gut. It doesn't matter what dimension you are working in, all of these properties hold for vectors. One is commutativity. A plus B is equal to B plus A. You can add those vectors in either order and you get the same result. Adding the zero vector to any vector changes nothing. Hope not surprising, right? If you have the vector A and then you go nowhere, you still have the vector A. The distributive property with scalar multiplication. If you want to multiply a sum of vectors by a scalar, the scalar distributes to the terms, CA, CB. There's also associativity of scalar multiplication. So if I multiply two scalars by a vector A, I'm allowed to do that in a different order. Oops, sorry. There we go. Associativity of vector addition. Again, very natural. If you do B plus C and then A, that's the same as doing A plus B and then C. Makes sense, right? A plus its opposite lands you with the zero vector, which makes sense. If I go this direction this far and then I go in the opposite direction, the same distance, it's like I went nowhere at all, right? That's the zero vector. You also have distributivity of vectors. So if you have a sum of two scalars, and then you wanted to multiply that by a vector, it works the same way as you would expect using distributivity. That's it. So A distributes to both of those two scalar terms. And then naturally, 1 times A equals A. If you take the vector A and you scale it by a factor of 1, you still got the vector A again. All right. Most of these properties are very easily proven geometrically or algebraically, so you should try. Just pick any one of these and try to do it geometrically, try to do it algebraically. It's very simple, very quick. I kind of said out loud how you would do some of them, in fact, like this one and this one. But what we'll do is we'll actually show the first property, commutativity, right? So commutativity is a nice one to keep an eye on because it comes from, or it's represented geometrically by what we call the parallelogram law. So here's u plus v, and here's v plus u, same vector. Or I should say travel along u and then travel along v. You get to the same place if you instead traveled along v and then traveled along u. Right? It's the same as going right there. So this is called the parallelogram law because it forms a parallelogram like so. Cool stuff. All right. All right, so now we need to talk about basis vectors. So basis vectors are very important. They simplify our lives in a lot of ways. So first, what is an actual basis? Well, by the axiom of choice, every vector space has a basis. This is not a trivial assumption, but if you look back into your Calc 1 notes, technically this is something we assumed way back before we started even talking about implicit differentiation. Not going to go into too much detail about the axiom of choice, but it's actually equivalent to this statement that every vector space has a basis. So what is a basis? A basis is really just a special set of vectors with which every other vector can be described using those special vectors, can be described through what are called linear combinations. So in other words, the basis vectors are special vectors where you can basically scale them and add them up, and that will give you any other possible vector you would want to describe. That's the idea. So those are called basis vectors. In 2 dimensions, in V2, the standard basis vectors are these two, 1, 0, 0, 1. Now keep in mind we're talking about vectors here, not points, right? So the vector I basically says to go 1 unit to the right in the x direction and no units in the y direction. It's this vector right here. The basis vector j says go 0 units in the x direction and 1 unit in the y direction. And that's right here. This is the vector j. And this kind of makes sense, right? It's basically like saying go 1 unit in this direction, in the positive direction along the x-axis or the y-axis. Naturally, it extends to 3 dimensions. So the basis vectors for V3 are I, j, k. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. There we go. And again, this doesn't need to stop at dimension 3. It naturally generalizes to any finite dimensional vector space like this, like Vn. So here's our first basis vector. In this case, there are n. Oops, maybe I should say 1, 2, 3, n. That was an n. There are n basis vectors. There are n components. We switched to the letter E just to kind of stand for identity. There's a 1 in the first coordinate slot. There's a 1 in the second coordinate slot, 1 in the third, ... 1 in the nth. And those are the standard basis vectors. So here is the big idea. This is what you want to take away from the idea of a basis vector. Every other vector you can imagine can be written in terms of these basis vectors. So if you've got a basis vector like 1, 2, 3, what we're saying is that you can write that vector in terms of the basis vectors I, j, k. So here we go. How about this vector 3, negative 1, 10? Well, this says travel 3 units in the I direction, negative 1 units in the j direction, 10 units in the k direction. So we can write that as a vector sum, 3i minus 1j plus 10k. There we go. That's why they're called the basis vectors. And this works for in general, right? So again, every vector can be written in terms of these basis vectors. So here is just an arbitrary 3-dimensional vector. And this process here shows that you can write it in terms of I, j, and k. These are just telling you basically which way to move along those coordinate axes. Cool stuff, basis vectors. All right, so this one I want you to try on your own. Here's 2 vectors. Let A be this vector, and let B be this vector. And I want you to try expressing this vector sum in terms of I, j, and k. All right? So first, think about how you're going to do it. Now, say something out loud to yourself. How would you start? All right, now try to work it out on your own. In the end, you should have a vector in terms of I, j, and k. Right, now let's do it together. Here we go. So I need to scale A by 2 and scale B by 3 and then add the results. So here is the vector A, scaled by 2. Here's the vector B, scaled by 3. And again, this just works naturally. This is just scalar multiplication. So we get 2i, 4j, negative 6k, 12i, 21k. There we go. Now what we're going to do is we're basically going to combine like terms. So we're going to get all the I terms together, and then we're going to get all the j terms together. There's only one. And then we're going to get all of the k terms together. And then voila, add them all up, and then we get this. Here, here, and here. And that's it. So 2a plus 3b is 14i plus 4j plus 15k. Okay. All right, so those are basis vectors. Next, we got to talk about unit vectors. So unit vectors are just vectors whose length are 1, whose length is 1. So a unit vector is a vector whose length is 1. That's it. What's nice about these types of vectors is that they only really encode direction. Because the length is 1, it makes it easy to discuss direction without having to worry about stretches and scalings, right? So for one, the basis vectors I, j, and k are all unit vectors because their length is 1. And you can kind of see that from the picture. You could also calculate it algebraically, and you'll see that it's obviously 1. Now, one thing that's nice is if we're given a non-zero vector, then we can, quote, normalize it. We can normalize the vector. So what that means is we can construct a vector that goes in the same direction as A, but has unit length. So in this way, normalization sheds away the scaling factor that is involved with a vector and just preserves the direction. That's the idea. So that's what normalization is doing. How do we do it? To normalize a vector, you just divide it by its length. Super easy to do, super straightforward. Let's say we've got a vector A, and we want to find a vector U that's a unit vector, and we want it to be in the same direction as A. We just find the length of A, and then divide A by its length, and we will have a unit vector in the direction of A. And here, this is me just verifying that the length of the unit vector is actually 1. So what is the length of this new vector? It's the length of this, which by properties of the absolute value, or properties of distance, we get this. Any real number divided by itself that's not 0 is equal to 1, so we have a unit vector. All right, so you try this. Find a unit vector u in the same direction as this vector a, all right? So think about it for a minute, how you're going to do it, right? And then compute it. See if you can compute this on your own. Unit vector in the same direction as a. All right, here we go. So first thing we need to do is we need to compute the length. So what is the length of A? It's the length of this vector here. Just use the distance formula. Just use that formula we saw earlier. Square each component, add up the results, and then take the square root. In this case, we get 3. So the length of A is 3. Now we're going to take this vector and just divide every component by 3. That's all you got to do. So multiply by 1/3, divide by 3, you get this, this, this. And so this is a unit vector that is in the same direction as A, but has length 1. So we've kind of like shed away all of the scaling involved with A. And now we're just talking about the direction of A. Okay. Next, last bit actually is a physics application. So naturally, you can probably imagine that there's a lot of uses in physics for vectors. For those of you that have taken a physics class that has vectors involved, this is probably going to seem very simple and very straightforward. We're going to explore them in much greater detail later on. So one of the coolest parts about this class is literally the last chapter, chapter 16, which is all about vector calculus. And that's really what you want to get into is vector calculus, because that's what lets you do all of the really interesting stuff that you've been maybe imagining for a couple years now. So yeah, they're used extensively in physics and engineering. A force is represented by a vector because it has a magnitude and it has a direction. So if you want to talk about a force acting on an object, the force comes from some direction and it has a certain size, right? If you've got several forces that are acting on an object, then the resultant force is the vector sum of all of those forces. So that's the resultant force. All right, let's try this example. Again, physics students, this will probably seem very familiar. So you can help out your classmates when we're doing the activities and help them with the homework and all that kind of stuff. Admittedly, I will say this really just boils down to right triangle trigonometry. That's really all it is. It's decomposing a vector into its component pieces and then working with right triangle trigonometry. So here we go. Let's say we've got a 100-pound weight hanging from 2 wires as shown in this picture. You've probably seen something like this and maybe had this thought and wondered about this before. Find the tensions, the forces, T1 and T2 in both wires, and find the magnitudes of the tension, like how much strength is involved there, right? That's the question. So first I want you to just ponder this for a minute. Think about how you could compute this. Look at the scenario, chew on it a little bit. All right, now say something out loud to yourself about how you could start. Remember, the goal here is you want to compute T1 and T2, given this picture. This is all the information you need to find what these two vectors are. Now try to work it out on your own. So try to write it down, see if you can compute it. This is one where you'll probably need a calculator at some point because these are not standard angles, right? So if you want to get like a decimal approximation, you're going to have to go to a calculator for those. All right, here we go. Let's do this one together. So by right triangle trigonometry, we can do is we can glean the vertical and horizontal components of these two forces. So I'm going to be referring to this figure here. And one thing I want to remind you of is that T1 and T2 are vectors, right? They are vectors. They are not real numbers. They're not scalars. They're vectors. So they're like arrows, okay? Um, but what we can do is we can write these vectors in terms of the standard basis vectors I and j. And this is where your right triangle trigonometry comes in, right? Because what we've got here is we've got a length. Oops, I wanted to do this, right? This is like the length of the vector t1, and this is the length of the vector t2. And what you can do is you can decompose this vector t1 into its constituent, or I should say its component values. Do this, right? So let's look at this piece by piece. So t1 is a scalar times I plus a scalar times j. Well, what is the scalar times I? What we need to know is what is this value right here? What is the size of this? What's the length of that line right there? This is where the right triangle trigonometry comes in, right? Because this line here is going to be the length of t1 times cosine of 50 degrees times cosine right here. Now in this case, this is actually negative because we're going in that direction. So we're going in like the negative x direction here. That's why this is negative. Now, how do we find this length right here? Well, we do the length of t1 and then we multiply it by sine of 50. So maybe you remember this from the past, right? It's like we're doing the cosine and then the sine here. And then this is the hypotenuse of this right triangle. That's really all that we're doing. We're using a right triangle to decompose this into left-right behavior and up-down behavior. And this is what it looks like for T1. All right, now do the same thing for T2. We need the length of this. We need the length of this. Here, oops, sorry. Here's that. And then here's the second thing. And now we have a way of describing our two vectors in terms of their component vectors, the basis vectors. Right. Yeah, there we go. All right, so now here's where the actual setup comes into play. The resultant tension, T1 plus T2, counterbalances the weight. So there's a weight here, W, that's pulling down on those two wires, right? It's pulling down on them. And because this tension, the two wires are holding that weight up, they're counterbalancing the weight. And what that means in terms of vector arithmetic is that if you add up these three vectors, these three forces, you don't go anywhere. You don't go anywhere, which is important, right? If this were not zero, then these wires would be not holding up the weight. They would be stretching. Yeah, in this case, they're holding up and nothing is moving. Everything is fixed, all right? Now, W is negative 100J because it's happening in the J direction and it's going down. So it's the J direction and the size is negative 100, or the signed size is negative 100, right? That means this is what the resultant tension is. So the tension T1 plus T2 is 100J. Now we can find everything. Now we're going to solve for T1 and T2 by solving for the lengths of T1 and T2. So I think that's what I have right here. Let me check. Yes, double check. Yes, yeah, exactly. All right, so this is just kind of doing some algebraic massage, right? So since we know that T1 plus T2 is 100J, we're going to write it in terms of its basis vectors. So this is the same as 0i plus 100j. No movement in the I direction, 100 in the j direction, and that's got to be equal to the sum of these two tensions. Now, we computed what these were earlier, and now we're going to move things around and combine like terms. So if I combine the I terms, or the horizontal components, and I combine the j terms, or the vertical components, then I get this. And this process should look familiar, maybe from something like partial fraction decomposition or solving systems of equations or something like that, right? But here's what we know. Look up here. We know that the scalar associated with I, the component of I, is 0. So if we compare coefficients, that means that 0 has to be equal to this. And then if we look at the coefficient associated with j, we know that 100 has to be equal to this. There we go. So these are linked. That's the idea. Those two things are linked. And that's where we get these two equations at the bottom. So what we end up with is a system of two equations involving two unknowns. The two unknowns are the length t1 and the length t2. But because we've got two equations, we can solve for both of those using elimination or substitution or a computational resource. And when we do that, we get this. So solving the system gives you that the length of t1 is equal to this, and the length of t2 is equal to this, and then we can go to a computer to give us an approximation. So the length of t1, is about 85.64 pounds, and this is 64.91 pounds, the length. All right, but now that we know the length, or the size, I should say, I should be calling it a size. Now that we know the size, we can actually write what the straight up vectors are, t1 and t2. We just go back to those previous equations we had right here. There's t1, the vector. Here's t2, the vector. There we go. And we get this. So now we have computed the actual tensions themselves, and we also know the lengths. We found those just a moment ago. All right, so there's one application. And on that note, let's play. So I'll see you all in class. We'll do an activity associated with vectors. Again, if you have seen vectors before, please assist your classmates and help your peers understand them. You might have a better intuition than they do already, but we'll gain a lot of intuition in this class as we go along. All right, well, I won't ramble on for too much longer. Thank you again for watching, and I will see you next time.